this for free at Graphmatica.com, or if you have another graphing application you use on your computer, that's okay too, but you want to be able to kind of show graphs, print them off, and turn them in. So that's what we're looking for here. So I'm going to graph this one. It's pretty easy. You just type up at the top here just the regular equation for the graph, y equals, you just put the whole equation in there. So y equals 2 cosine of 2x plus 2x. So remember that was the first thing we had. So it looks something like this. So we'll kind of graph them in different colors. Up here you can zoom out or in if you want to see it. You can click on zoom in, zoom out, things like that. If you want to graph another one in the same coordinate axes, you just type another equation. So now I just start typing the other equation, y equals sine of 2x plus x squared. Remember here we were using c equals 0, so I don't have to put on a c, a constant. And then I'll enter on that one, and then it will graph that one as well. So you can kind of see the two graphs here. Now the one thing I do want you to explain is what the question asks. Why is the answer reasonable? So let's think about that for a minute here. Remember, these were our two equations that we had. Remember, when we integrated this, we got the sine of 2x plus x squared, right? So the relationship is really that this is basically the original function and this is its derivative, right? Does that make sense? So when I took its antiderivative, I got back to the original function. Here, this one is actually its derivative. So when I look at the graph of this one, I should be able to see that it's reasonable that this becomes its derivative. This graph is the derivative graph. So let's look at those two on Graphmatica and see if that makes sense. So the original one is this one. It's kind of like highlighting it. This is the sine of 2x plus x squared is this black one here. So when I take its derivative, what kind of things should I see? For instance, in this first left-hand part, when I see that the function is decreasing, what should be happening in its derivative? What kind of values do we get in the derivative if the function's decreasing? What should they be? Jeff is thinking it. Yeah. They're negative, right? Because remember, a derivative is all these slopes. Those slopes are all negative. So notice down here, its derivative has all negative values. Notice what happens right here. What happens at the very bottom of this little curve? What kind of slope does it have right here? 0. And notice the pink graph hits 0, right? So that's why it's 0 there. And then as we start increasing on the black graph, notice the pink starts to be positive values. So those are the things you kind of check to make sure it's reasonable. So I'm looking at the original function where it's decreasing, it should have, the derivative has negative values. Where it has a 0 slope, the derivative has a 0 value. Where it's increasing, it has positive values. So I do want you to write, if it says to check the answer is reasonable in the problem, write some sort of explanation. Why does it make sense when you're done? So in a graph from Graphmatica, in order to print this off, you can actually print it just like this is. I tend to copy it and put it into Word and then label the graphs. I do want to see what graph is which. So make sure you've labeled them somehow. Usually what I do is just copy the graph color. I'll usually use the color that it uses, and then I'll paste it into a Word document. I pasted this one earlier into a Word document, looked like this. I just went up here and filed copy paste. So it looks like that, so that underneath it then I can label in the different colors which one was which. So just make sure you do that, and you don't have to type it. If you hand label, that's fine with me. But do make sure that you've highlighted them in different colors. If you can't print in color, people have used color pencils or colored pens to put them in different colors and then label them that way, and that's fine too. So if you want to print in black and white and then label them with different colors and draw them with different colors later, that's totally fine. So just make sure you do that and include again some of your work. Make sure you show your work here and explain why the answer is reasonable. Okay, so it should look something like that. The other thing I'll show you on Graphmatica is just the second piece is, what if you want to look at a graph but only certain parts of it? like you want to restrict its domain. I only want to look at it between like -1 and 5 or something like that. So this is, if I'm going to just show you an example of how to do a piecewise function. Have you seen piecewise functions before? So they have these little different pieces. So you can do this on Graphmatica too. I'll show you the format for the notation. So if I want to graph y equals x plus 2 squared, on Graphmatica they use an up arrow like that for doing squares or exponents. So you can just put it in like that. So notice on this one I want it to be from x is less than -1. So basically I want it from -infinity, right, up to -1. I want to show this piece of the graph. So to give it a particular domain in Graphmatica, you start with braces, and then you use like parentheses and those type of notations for these. So on this one, when you do the notation for -infinity, you actually kind of leave it blank for -infinity, and then you go up to -1. And I use a parentheses around -1 because I don't want to include it. So again, it's not equal to -1, so I will use a parentheses there. So they don't use an infinity symbol, they tend to just leave it blank, but that's kind of the notation in Graphmatica. And so then I would graph y equals 5, and if I want to do that between -1 and 3, again, you put the domain in braces, and I would want to from -1 to 3. So I want to include -1 on that one, so it has a bracket, so that's kind of like interval notation, but a parentheses around the 3. Okay, so that's kind of the syntax they use in Graphmatica to get those different domains. And then for 3x minus 4, I'd put in the equation, and then I'd have these braces from 3. Let's see, 3 would have a bracket, and then 7 would be a parentheses. Okay, so that's kind of the syntax they use on Graphmatica to get those different things. They basically use interval notation, but to separate it, they always put it in the braces for particular domains. So let me show you that as well on Graphmatica. Everyone got that written down? I'll switch over. Okay. If you want to get rid of these graphs I already have, you can save different files, but I just go up here under Edit. You can delete. That's where copy is, but I'll just delete everything I have for now. Okay, so here we go. So here's y equals x plus 2 squared. And then again, you do the braces, and then you basically, -infinity you don't put in there, but do a comma and then to -1 and close the braces there. So notice, hopefully recognize x plus 2 squared is a parabola, right? So notice it's coming here from -infinity, and notice it stops here at -1, has an open circle there because it doesn't include that point. It's strictly less than -1, so it looks like that. So there's the first part. Then you just type in the next equation, y equals 5. What kind of equation is, or what kind of graph is y equals 5? Yeah, that's going to be a horizontal line at 5, right? So it's just a horizontal line. So that's what we should see on that one. So let me see if we can get that. So there's that one there. You can see it here in this very light blue. It's kind of hard to see there, but there's the horizontal line at 5. Notice it starts at -1, so there's a closed circle there, but it doesn't include 3, so there's an open circle at 3. And then the other equation is y equals 3x minus 4. And let's see, we went from 3 to 7 on that one, right? Okay, so again, I just put that in braces behind that, and I enter on that one. And so now you can see that in kind of the bright green graph. So it actually shares this point, so it fills it in on the left. Notice you can't kind of see the right-hand side, so I'm going to zoom out one time. There you can see it a little bit better. So I just zoomed out, and then I can see here it stops at 7, has an open circle there. So like something like that. So that's just to get you to practice kind of the notation, how you need to do it. Again, you can go up here and copy that and then paste it into a Word document. I'll show you what mine looked like. Mine looked like this when I did it earlier. So I just pasted that into the Word document and again labeled my equations down here with the different colors. So that one, there isn't much calculation to do, just practice sort of graphing. Make sure you getting comfortable with that. So that's Graphmatica. It's pretty easy to use. You can kind of come up, look up here. There's different option settings you can put it on. I usually just use the basic one, but zooming in and out will help there too as well. Okay, any questions on either of those? So there's a short Graphmatica assignment on that is posted on Canvas. It's really just like these two problems. I want you to force you to kind of practice that a little bit. So make sure you do that for Friday. So that will be due on Friday, those two problems for the Graphmatica assignment. Yep. Yep. So those will be ones you print off and just include your work if you have a need to do, like to get the integral or anything like that. Yep. Okay. Any other questions on that? If you do have any issues with Graphmatica, just let me know and I can help you with that. So today we're going to start the first part of 7.1. I will collect the homework, but at the end of class today. So we're going to start the first part of 7.1. So all we've been doing so far should have been review. Hopefully, mostly, maybe not the Graphmatica, but all the other parts of the integration. So I hope you didn't struggle too much with it, because really at this point we're assuming that you kind of know those concepts. So hopefully that kind of helped you remind yourself, how do I do this substitution? How do I do these rules? Do I remember them? And hopefully at this point you do, but if not, make sure you take some time to go back and really get those down, because those will be important moving forward from here. We're going to assume that you know those. So that's important to make sure you've got those down. So in chapter 7, we're going to start the new material. It is all going to be about integration. So we're going to do more integral techniques. And so I'm going to show you a new technique here called integration by parts. So substitution is one important method, but this is kind of the second important method called integration by parts. There are many things that we can't integrate using substitution, so we need some different methods. So we're going to look at that here in integration by parts. To give you an idea about integration by substitution, when we integrate using substitution, we basically undo the chain rule. So to go backwards, we would use what we call the chain rule. You would take the derivative of the outside times the derivative of the inside. And that's what a substitution does, is undoes the chain rule. So integration by parts actually undoes the product rule. So if you're familiar with the product rule, that's what it undoes, is going to be the product rule. So that's what we're going to look at here. So let's go ahead and take a look at that for a minute. We're going to be looking at how we do this, the product rule. So actually, let me write that first, and then we'll kind of undo that. Okay, so here's our product rule. So remember, when we have f times g, and we want to take its derivative of some f times g function, they're both functions of x. The question is, how do we do it? Who remembers the product rule?
First times the second plus the second times the first.
Okay, so the derivative of the first times the second plus, what did you say? Right. Did everyone learn it that way? F prime g plus g prime f? Sometimes you can mix those around, so you may have learned it in a different order, but that's what we're going to be looking at here. So we're going to kind of change it around, and we're going to use some different symbols called u and v. So we're going to call these f, g, and g prime f. So we'll first use the f and g, but we'll do a substitution here in a minute, or label them with different things. So what we're going to do now is actually integrate this. So we're going to take the integral of both sides. And I'm going to go ahead and put the f of x's parts in there this time. Okay, so we're going to integrate the left-hand side. And then we're going to integrate the right-hand side of the product rule as well. So that's kind of the short version, but I'll put in the x's this time. I'm actually going to write the f of x first, but either way is fine. Okay. So this is what the product rule says. If you differentiate f times g, you get f prime g plus g prime f. So that's our rule. We know that's true. So we're going to integrate both sides. Notice here we've got f prime g. I put the f of x first, so I did f g prime, but those are the same thing. So we're going to integrate both sides of this. Now when you integrate a derivative, what happens to it? Cancels, right? So we integrate a derivative, it's like undoing the derivative. So all we get left over here is f of x times g of x. Okay, so that's what we're left with here. No problem. On the right-hand side, I'm going to separate them into two integrals. So they're separated by addition, so I can separate those into two. So one will be f prime g, and the other one f g prime. Okay, so I'm just kind of showing you where this integration by parts rule comes from. Okay, so now we're going to kind of I'm going to just kind of switch the equation around a little bit, and then I'm going to label the different pieces of it. So in this one, we're going to actually solve for this piece right here. So what I'm going to do is subtract this to the other side, but I'm going to move this one on the left. So here's what it's going to look like. I'm going to separate this out here. So I'm going to write it by itself, the FG prime. And if I separate this, it will be equal to the f of x g of x minus this piece here. Okay. So I just kind of isolated this part of the equation, moved this to the left by subtracting, but I did kind of switch the sides they were on. Okay, so here's what we're going to do now is I'm going to label them as parts called u's and v's. And that's the notation they use in integration by parts. So what we're going to do is we're going to call out f of x. We're going to call it a function u. Okay? So everywhere there's an f of x, that's going to be called u. So here's another one, so that's also u. Now when I see f prime of x, I'm going to call this, actually I'm going to put it together with this. So I'm going to hook it up with the dx, and so that's actually the derivative of u, and I'm going to call it du together. So when I take u, its derivative is u prime, or we can call that du. So this piece of f of x with dx would be called du. Okay, so those parts are u and du. All right, now g of x we're going to call v. Just sometimes a little tricky to differentiate in your writing, so hopefully you'll do that. So that one's a v. This is also a v down here. So there's a g of x there. That's a v. And what do you think I'm going to call this g prime dx? dv. That's right, the derivative of v. So that's dv. Okay, so sitting right here is this formula called integration by parts. I'm going to write it first in that notation, and then we'll write it formally underneath. So this formula is the integral of u dv is equal to uv minus the integral, and I'm going to put the v in front of, so it will be v du. This is the integration by parts formula. And it basically undoes a product rule. But the pieces are, you have got to figure out what is my u, what's my v, what's my du, and what's my dv. So there's actually 4 parts to integration by parts. That's what they call integration by parts. There's 4 different pieces. In your original integral, you'll have to identify which part you want to be u and which part you want to be dv. From those 2 parts, you will be able to identify the rest of them. So once I've identified what those are in my original integral, I'll have to go then find, well, what is du and what was the original v? And then you'll be able to fill in the rest of the formula. And that's the idea behind integration by parts. So let's write it formally here. This is the formula for integration by parts. And then I'll show you an example of how we use this. So, and you will use it a ton, so you'll probably have it memorized. Really, most people memorize the right-hand side, so because that's what your result will be. It's the uv minus the integral of v du. That's what those are the pieces you'll fill in for your result, basically. Okay, so let me show you how you would use this. Okay, so you've got an idea here. Everyone got that written down, hopefully? Yeah? Got it? Okay. So let's go ahead and try one here. We're going to do this one. We're going to find the integral of x e to the x dx. Now, this is an integral that if you tried to do some sort of substitution, it wouldn't work out very well. So if you let u be like x, the derivative is 1, so it wouldn't match up to the other piece that's in there. So this is really impossible to do by substitution, and we don't have a formula for x e to the x. Notice there's a product in there. A lot of times when we see products like this, this is a case where we might use integration by parts. So here's what we're going to start with. I'm going to rewrite this, and then I'm going to write the formula underneath so you know what we're kind of shooting for here. So remember, this is our formula. is the integral of u dv is equal to uv minus the integral of v du. So my first step is always to look at the original integral and decide which part is going to be u and which part is going to be the dv. There will always be two parts to the integral because a lot of times it's a product. So the two parts I really see here are an x and an e to the x. So I'm going to identify what each of these are, those two parts off to the side. Okay? Eventually you're going to have to identify four parts, but we start with the first two are always u and dv. Now, there are some reasons we choose one over the other to be a certain part, but for now we're just going to choose kind of the order they've given it to me here. So I'm going to let u be the x part and the dv be the e to the x. And dv will always include the dx because it's a differential, so the dv part always takes the dx with it. Okay, so in the original integral you have to identify u and dv, those two parts, and they have to take up the entire integral. There can't be pieces left over that you didn't use. So you have to use the whole thing. Okay, now underneath this you want to identify the other two parts. The other two parts are always du and v. The derivative of whatever you've chosen u to be and the integral of dv will be v. So from those two you've identified, we can find these two, right? What's the derivative of u equals x? If it's x, what's du? Yeah, a 1, right, with a dx. So 1 dx. If you know dv, how do you get back to v? Take the integral, right? So now you've got to integrate e to the x. What is the integral of e to the x? E to the x. That was an easy one, right? Okay, good. No, and I'll tell you why in a minute, but basically we will add a plus c, but only at the very end of our answer. So in these parts situation, you don't have to add any plus c's. You will do it at the end of your answer, though. Okay, so now let's fill in the pieces. So my integral ex e to the x dx, I've set that up as my u and my dv. Now I fill in the rest of these pieces to figure out what it's equal to. So I put in the u, so u was x, the v was e to the x, and then I'll have the integral of the v, which is e to the x, and then plug in the u, which is dx. Okay, so it's important that you set up these four parts so that you can then fill all of the four parts in. So I fill in what is u, what is v, and du. Okay, now this is what this integral is equal to. Is that a final answer? No, I see an integral still. So when you use the integration by parts formula, it gets me close to the answer, but the last piece is you still need to integrate that. And so here's one way you can tell if you've done it correctly. Can you integrate this? So if you get something you can't integrate, that's going to be an issue. So can I integrate e to the x? Sure, easy, right? So let's do it. So my final answer is just to integrate that piece. E to the x, the integral is e to the x. And at the very end here, on my final integration, that's when I'll add the plus c. So technically there's one here, but we just do it on our final answer. And so this is the integral of x e to the x. That's how integration by parts works. And remember, to check integration, to go back, I would have to take the derivative of this and make sure it was this. But that would involve a product rule, right? So that's why we're undoing sort of a product rule when we use integration by parts, is the idea behind it. Okay, so that's the basics. That's a real basic one to kind of get you started with how to do the pieces. Questions on that right now? Doing okay? Okay, let's make a couple notes. So notice what's kind of important as we begin is identifying the u and the dv. Those are what you have to choose out of your integral. Once you set those two up, du and v you find yourself based on what you've chosen for u and dv. And then it's just a matter of filling in the formula, the different pieces. Notice I don't actually ever do a substitution here. All I do is identify the parts and then fill them in the formula. So I don't technically like put in a u or a du. I'm following a formula by filling in those pieces I've assigned. So that's kind of why we say this isn't technically a substitution. So let's make a couple notes about integration by parts. Number one, you only need to add that plus C at the end of your answer. So that was a good question that Joel asked. You really don't need it in any of the parts. You can just do it at the very end if it doesn't have limits anyway. When you use du and dv and set those up, they should include always the dx or the differential. I'm saying dx, but whatever the variable is, it's w dw, but those should include the differential dx or whatever it is according to the variable. And one other note is after you fill in the formula that you still need to integrate. So I'll write that here. So after you fill in the formula, you need to integrate to get to your final answer. So don't forget, the formula won't give you the answer. You still are going to need to integrate after that. And hopefully you set it up right so you can integrate that last piece. Sometimes you'll find if you choose u and dv incorrectly, like maybe you've done the wrong order, which should be which, you'll find you'll get a complicated expression you don't know how to integrate. That's sometimes an indication you should go back and check, did I set this up right? So that's a couple notes I want to make about u and dv. Last time I just chose them in the order they gave them to me, but there is a certain way you should choose them. So number one, you should always choose u so that the du is simpler than what it started as. So remember, if you choose u, you're going to have to take its derivative. So if I choose u, I want to make sure its derivative du should be a more simpler expression than the u was. If it's getting more complicated, that's going to be harder to work with. So you do want to choose it so it's simpler than what you started with. That's why x is a good choice, because its derivative is really simple. It's a 1. And so that is a good choice for u. Now, when you're choosing dv, you have to remember that that will need to be integrated. So you have to make sure you choose dv so that you can easily integrate it. So usually we'll choose dv to be the most complicated part. But just remember that dv must be integrated. So if you're looking at dv and you don't know how to integrate it, that's going to be an issue. So that might not be the best choice for dv. It does tend to be the more complicated part than u, but you have to keep in mind you are going to have to integrate it. So, okay, so sometimes the hardest choice is which, but as we practice, you'll kind of see that certain functions you start to see, like x or x squared, they have simple derivatives, so they tend to always be used. Things like e to the x are easy to integrate, so they tend to be the dv parts. And we'll see some other functions start showing up more often and recognize how to put those in the different places. Okay, so now we're ready. Let's try some more integration by parts. Should be fun. So we're going to look at this one. This is the integral of x cubed natural log of x. I always encourage you to try other techniques first if you can, but this is another case where substitution will be difficult. There isn't an obvious u and du in this one, and we don't have a basic rule I can use either. So this is a good candidate for integration by parts. So remember, the very first step is to choose your u and your dv. Okay, so that's what I start with. So I have x cubed and I have natural log of x. Okay, what are you guys thinking? Which one do you think should be u? X cubed, okay. It does have a pretty simple derivative, right? But let's think about this. Then dv has to be the natural log, right? Do you know how to integrate the natural log? Wait a minute, no. You know how to do what with the natural log? You know its derivative, right? But I don't know any rule to integrate the natural log, do you? Okay, so that right there, I'm not saying x cubed wouldn't be a good u, but I don't want it to be dv. So I'm going to choose it to actually be the u, because I know it's derivative, but I don't know how to integrate. Could I integrate x cubed? Yeah. So I know how to integrate x cubed, so I think at least it's doable. So here's one hint. If you have a natural log, it's pretty much going to have to be u, because you don't know how to integrate it. So that's your choices. And don't forget the dv then, the x cubed would go with the dx part. Okay, so now remember underneath you're going to find the other two parts. Okay, the du and the v. So let's start with du. What's the derivative of natural log of x? 1 over x. What else should it have with it? No absolute value, but a dx. There you go. Remember, du and dv should have dx. That's right. So it's 1 over x dx. What's the integral of x cubed? Yeah, 1/4 x to the 4th. Good. Now, the hardest part about integration by parts is you have to go both directions. You have to differentiate and you got to integrate. So you got to keep those rules straight. So sometimes that's hard for students. Okay, once you've got the 4 parts set up, you're going to fill in according to the formula. And you can write that several times, but it's uv minus the integral of v du. So this integral of x cubed natural log of x will be equal to dx there. Okay, so I fill in the pieces, right? The first one, the u is ln of x times the v, which is 1/4 x to the 4th, minus the integral of 1/4 x to the 4th. There's your v, right? And it's being times by the du. What's du? 1 over x dx, right? Okay. Okay, so you got it so far. I put in u, I put in v, minus the integral of v, 1/4 x to the 4th, and the du here is 1 over x dx. Okay, are we done? No. You've got to integrate this, right? Can I integrate this? Yeah, probably not like this, but isn't there a bit of simplifying I could do here? Like, what's x to the 4th over x? X to the 3rd, right? So let's do that. And also, at the beginning here, I'm just going to put this in front of the natural log, because that's a little bit better format instead of behind it. But that's 1/4 x to the 4th natural log of x. So I really need to integrate 1/4 x cubed dx. So that's one thing. If you have something with du and v, you may need to simplify those a little bit, and then you can integrate. So this shouldn't be too hard to integrate, right? Let's see what we get. So we get 1/4 x to the 4th natural log of x minus, what's the rule for x cubed? What's it going to become? X to the 4th over 4. So actually, what fraction is going to be in front? 1/16. There you go. 1/16 x to the 4th. So remember, you add 1 to the power, and that makes it 4, and then you divide by another 4, so 4 times 4 will give you 16. And this at the very end is when we put on the 1 plus c. Okay, so we get 1/4 x to the 4th ln of x minus 1/16 x to the 4th plus c. And that's your final answer. Okay, questions on that? Integration by parts, kind of fun, right? All those parts are kind of working together. I like those a lot. This is one of my favorite techniques. I actually like it even better than substitution sometimes. So, all right. Maybe you're thinking, what is she? She's crazy. Okay, that's fine. Say that later, but just not in front of me, okay? Okay. All right, so let's look at the next one here. We're dealing with a different variable theta, but it's still the same idea. So remember, the very first thing you're going to start with is identifying u and dv, the two parts in your integral. So I see here basically it's theta, and then there's the secant squared, right? So let's think about this. So think about theta, think about secant squared. squared. Which one is easy to integrate or take its derivative of? Let me kind of go to some of the outreach centers there. You guys have been kind of quiet today. So Jonathan there and Haley, what do you think? Would you choose to be the u? Do you think theta or secant squared? Okay, for you? Well, let's try it and see. Oops, not with the d theta. So then this would have to be your theta d theta, right? Do you know how to differentiate secant squared? Yeah, we do, but it's fairly complicated. What is the derivative of secant squared? It's kind of a chain rule, right? You got to do the power. It's 2 secant theta times, what's the derivative of the inside? Secant tangent, right? The derivative of secant is secant tangent. So you got to do the power rule on the outside times it by the derivative of the inside. Does that look like it's getting simpler? That seems a little bit complicated. Like, I don't want that to show up in an integral because I'm getting crazy there. So that's an indication maybe we should switch this around because it seems to not be getting much simpler. And that's okay to try and just see what happens. So what if we switched it around? So we said this was theta and this was secant squared. Okay, let's see if we can get some things we can do here with du and dv. So remember, once you've assigned those, then you find du and v. So let me go over there to Kimberly. Is Lindsay, you're there today, right? Okay, Lindsay, what's our du going to be if that's our u? Yep. Good. And let's see, Clayton, what would the v be? Do you know how to integrate secant squared? Very good. So we do know how to integrate secant squared, right? That gives us the tangent theta. So that's a nice choice because it does have a nice integral. It becomes the tangent. Okay, so things are looking pretty good so far. We got a simpler du. It was easily integrated. So let's go ahead and follow the formula now. So you got it memorized yet? The integral of u dv equals uv minus the integral of v du. Okay, so filling these in, if we fill in uv minus the integral of v du, Ethan and Kimberly, why don't you help us with that? What is uv going to look like? Yep, good. Minus the integral, Ethan, what's v du going to look like? That's exactly right. Very good. So filling in those pieces, he got theta, tangent theta, minus the integral of tangent theta d theta. Looking good so far? Okay. So the last step is, ask myself, can I integrate tangent theta? Yeah. So whenever I ask you about a trig function, remember we have formulas for all 6 trig functions now. So you may have to look it back up in our integration review. But what's the integral of tangent theta? Who remembers that one? Natural log of secant theta. That's exactly right. Yep. So you may have to look that up, but the integral of tangent is natural log of the absolute value of secant theta. And then we'll put on the plus c. Good. So that's exactly right. And so this is a case of us really thinking about u and dv, and you may need to on your homework, which is going to be which. And you may try one and get something that's more complicated than you expected. If you do that, maybe go back and kind of switch what you thought u and dv were. And that's okay to do if you start getting more complicated than what it started as. Okay. All right, good questions on those. Anything else you want to ask about on this? Looks like you're filling those in correctly. Okay, let's try this one. Let's try the integral of sine inverse of x. If you like the notations, arc sine of x, basically, dx. Now, this is interesting because you may look at this and be like, there's not 2 parts to this. There's like the sine inverse of x. What's the other part to this? Yeah, the dx, the differential. That's right. That's the only other piece we have. So one piece is this arc sine, or sine inverse of x. The other piece will just be the dx. Okay, that's the other piece. So the question is, the main part is the arc sine. Do we know anything dealing with the arc sine? Do you know its derivative? I think that's the only thing we know, right? We don't know its integral, otherwise I could use it here. So I think you have to let that one be u, because the only thing we know about the arc sine is what its derivative is. So the other part is really a 1. It's a 1 dx. So that can be our dv. So don't be afraid if you don't see two parts. Really, the other part is like a 1. 1 dx, or however you want to write that. Okay, so those are our two parts. Who remembers the derivative of the arc sine? That's probably something you got to look up. Jeff, you got it? It is 1 over, it's actually the square root of 1 minus x squared. Anyone remember that? They're like, yeah, I got that one. Okay, or you can look it up if you need to. Okay, the v is going to be where you integrate just a dx, right? What's the integral of dx? X, because it's really like a 1, right? The integral of 1 is x. Good. Okay, so let's set this up. So write the formula again. So our integral of sine inverse of x dx is equal to, let's see, is Trenton there and Kimberly today? Yeah? Trenton?
Yes.
Okay, awesome. Help us fill in uv. What would we have there?
So you're going to have sine inverse of x.
Yep.
Times x.
Good. And then what would you have under the integral, Trenton?
So you're going to have, so x, and then 1 divided by the square root of x squared.
Yep, good. All right, good. So he put in the u, the v, minus the integral of v is, again, x, and then du is all of this, 1 over the square root of 1 minus x squared dx. Okay. So just kind of cleaning this up a bit, I'll put the x in front again, x sine inverse of x. Now this is just a fraction, right? We can write this as 1 fraction x over the square root of 1 minus x squared dx. So the question will be, can I integrate this? What do you think? David's saying yes. You can, right? How are you going to integrate this? Yeah, you're going to have to use a substitution. So here's integration by parts, but within it, we're going to have to do a u substitution on this one. What would you let be u here? Yeah, 1 minus x squared, the inner part, and the du. I'll use like a capital U if you want to differentiate from the ones we used up there, but it doesn't matter. You can use a t or some other variable if you prefer. So if we let u be 1 minus x squared, then u is negative 2, du is negative 2x dx. And that will match up the variable part to the other part of the integral. So this is a good candidate for substitution. We just need to adjust that negative 2, so we'll have to divide by the negative 2 when we substitute. Okay, so I'll go ahead and do the substitution. You can do that right within it if you want, or you can do it off to the side to see what that will be. So I'll kind of do it off to the side here. So I'll have a negative 1/2 du over basically the square root of u. Right? The x dx is all part of the du. This is the square root, and that's the u part. Do you know how to integrate? If it has the square root of u in the denominator, how do we write that? Yeah, u to the negative 1/2, right? So then you can just use a power rule. So that should give me negative 1/2 u to the, what will the new power be? 1/2, right? Positive 1/2 if you add 1, and then you'll have to divide by 1/2, which will cancel those out. So I basically get negative u to the 1/2. So that's negative 1 minus x squared to the 1/2. Okay, so don't forget, you do have to put the u back in here. Here our final answer should be in terms of x. So I'll just go write my final answer here. Don't forget I have this first part, x sine inverse of x. And it looks like I'm going to have minus a minus, so I believe that becomes a plus. plus 1 minus x squared to the 1/2. And that's my final answer. So notice I have minus the minus, plugging that in, so that'll become a plus. And you can put on a plus c here, but I usually just wait and put it on the very end. Okay, how we doing? Is that one okay? Got this idea of integration by parts? Awesome. So we might get something like this, but you can still integrate that. So as long as this is an expression you can integrate, even using substitution, you will probably have set up your parts correctly there. Any questions on that one? Okay, let's do, this will probably be our last one for today. So we'll do one more for today, and then you should be able to do the first part of your homework in 7-1. So, okay, so this one actually has some limits on it. The limits work just like I normally do. We integrate it, and then we're at the end. We'll just plug in limits instead of do plus c. So we're still looking for our two parts, u and dv. So the pieces I have are w, or w minus 2 to the 4th dw. I don't know. You can probably integrate and differentiate both of them, right? Which one should we try as u? Any thoughts? We just go with the w. This is probably the more simpler part, right? Let's try that and see what happens. So what if we let that be w, and this w minus 2 to the 4th? Okay, then we got to find du and v. So let's go to Austin and Kimberly. If this is w, what's my du going to be? Yep, dw. Excellent. And then if we integrate w minus 2 to the 4th, well, sometimes this is hard for students to think about. Can I integrate w minus 2 to the 4th? Actually, you can probably just use a power rule, right?
So it'd just be w minus 2 to the 5th over 5?
That's exactly right. Yep. That's all that is. So you can apply the power rule here. Technically, you might have to do a u sub to get your answer, but here's why I didn't. If the derivative of the inside is just a 1, there's no adjustments you're going to need to make, like divide by a constant or anything like that. So a lot of times if the derivative of this is inside, you can just do the basic power rule, and that will give you the correct integral. But you can only do that if the derivative of the inside is 1. So just watch out. Otherwise, you should probably go through substitution. So, but that one worked out okay. Okay, so let's fill in the formula here. So we've got the integral of 0 to 2w minus 2. Okay, so let's fill in the pieces. So our u, that's going to be w, right? V is w minus 2 to the 5th over 5 minus the integral of, and that's a 2, sorry. The integral of v, which is w minus 2 to the 5th over 5. But the nice thing, du is just dw. Okay. Are we okay? Am I going to be able to integrate this piece? Yeah. Probably just another power rule, right? So let's do it. There was nothing in there with it except a dw, so that should be okay to integrate. So let's apply another power rule. What will the new power be? w2 minus 2 to the 6th, right? Can you tell what the denominator is going to be? You got to divide by 6, but 5 was already there, so what are we going to have? 30. That's right. Okay, and then instead of plus c, I'll just plug in the limits from 0 to 2. So this is just another power rule. Add 1, divide by the 6, but the 5 was already there, so that becomes 30. And then you just plug those in and simplify. Now this seems like it might be hard, but I noticed something's going to happen when I plug in 2. What's going to happen when you plug in 2? A bunch of zeros, right? Like this one is 0 and this one is 0. So those both zero out. And actually one of these, when you plug in 0, is also 0, right? The first one? Because you're going to multiply it by 0 in the front. So that is also 0. So you really only have one fraction here in the end. The 0 minus 2 to the 6th over 30. So this is 0, that's 0. There's a 0 in front of that one. So basically here you just have negative 2 to the 6th over 30. And this minus a negative will become positive. So what is 2 to the 6th? That 64? 64? So 64 30ths or 32 15ths? Yeah, so you can do them with limits as well. You just put the limits in. I usually wait till the very end and then apply the limits to whatever I get there. Okay, well that's where we're going to stop for today. We're going to do some more with this on Friday. Remember, we don't have class tomorrow. So just a reminder, you've got the Graphmatica assignment, and there is now the first assignment out of the textbook that are due Friday. So the Graphmatica assignment has those two problems. You got to print those off. And then on Canvas, there's the 7.1 Part 1 assignment, and it lists out the problems on Canvas, which ones to do, okay? So those will both be due on Friday. Okay. Doing okay? Ready to go? Okay. If you want to stick around and ask me a couple questions on the homework, you're welcome to. Otherwise, just leave your homework at the end of the row, and I'll collect it on my way out. For those of you in the Outreach Center, Jonathan, just make sure you get that scanned and emailed to me. Or take a picture and email it to me that way, okay? Oh, I forgot to send around the attendance. Well, here's what at the back, and if you just initial by today,